My pleasure to introduce Andrew McCallum. This is, in fact, a sadly out-of-date title slide because he is no longer exactly at these places. He's taking up a faculty position at UMass Amherst starting in the fall. But before that, he was the VP for Research and Development at Whiz-Bang Labs, which was the most interesting company out there doing machine learning and information extraction. And he'll tell you about all the projects he did there, and previously at Just Research, where he built, among other things, a search engine over computer science papers on the web, and the predecessor to SiteServe. I can tell you about what he did before he got to Whiz-Bang, which included a PhD at Rochester, a postdoc at CMU, and quite a lot of code writing. Andrew, in addition to contributing to various new projects like Guile and Emacs and GCC, and being the project leader for the GNU Objective-C library, and writing a heck of a lot of code at Whiz-Bang. Also as the author of the Reinforcement Learning Toolkit, a couple of virtual reality simulators, and what am I leaving out? Oh, Lipo, which is the bag of words library if you want to do IR or text classification based on bags of words. So all of this code, I think, is pretty much out there. You might want to talk to him after it, in addition to about, you might want to talk to him about it after this, in addition to talking about this stuff. The code training team might be particularly interested in talking to Andrew because he has done more than code training also other stuff. So, Andrew McCallum, welcome.
Thank you very much. Very generous introduction. Yeah, I'm thrilled to be here. Thank you for inviting me. I've known about the workshop sort of in the periphery, but not known that much about it. And now that I've gotten to come and visit and learn more about it, I'm thrilled, actually. Gosh, I'd love to come. I don't know. So I'm going to describe today some joint work with many people. Most of it is with John Lafferty and Fernando Pereira when all three of us were working at Whiz-Bang Labs. And some of it is also with David Bly and Drew Bagnell, who were summer interns of mine at Whiz-Bang last summer. So one of the grand old dreams of artificial intelligence is to build large knowledge bases and reason with them and and make inferences from them and things like that. And the problem is that filling and maintaining these large knowledge bases is very difficult and time-consuming and fraught with problems. I mean, poor Doug Lennet, you know. I can take an aside here to maybe just a few jokes. I mean, I was actually at the machine learning conference in '91 when he was apologizing for us for having exited from the machine learning research community for just a couple of years because he felt it was really important to build a system with common sense, and that he promised that he would be done with the system in just another year or two, and then he would be coming back. And here it is, 15 years later, and he's still banging his head against the wall. And anyway, so building large knowledge bases is incredibly hard. The web is the world's largest knowledge base, and it's being constantly maintained by literally millions of people. It's a wonderful thing, right? I mean, all of us know what a wonderful thing it is. The problem is that it's in a form intended for human consumption, not for manipulation and mining by computers. It's not in a database form with objects and slots and relations and things like that. Information extraction is the process of taking text intended for humans and using it to fill slots in a database. And that's what we'll spend most of the time talking about today. Information extraction historically has been performed mostly in the context of things like the DARPA MUC message understanding conference tasks. Newspaper articles with grammatical sentences in flowing paragraphs with not that much formatting information. So the web is quite different, right? It often consists of many snippets, ungrammatical snippets. But on the other hand, the formatting information there is very rich and powerful. And some of the techniques that I'll talk about were inspired by the desire to build information extraction systems that could simultaneously take advantage of language features in these snippets and also the formatting information that's on the web. So first, I'd like to talk about a few examples of information extraction from the web that we worked on while we were at Whiz-Bang Labs. And then I'll talk about a few models that turned out to do a good job at being able to capture these formatting features, and also these models turned out to be quite good at doing tasks that are like the traditional grammatical muck tasks as well. All right. So Whizbang's first project was to extract job openings from company websites. You would start at a company homepage like this, find the links and follow the links to get to the area of the website that lists job openings, and then automatically segment the job openings from each other and automatically extract the job title, description, contact phone number, location in the country, and so on, and populate a database like this. We wrote a system to do this, filled a very large database, actually gathered about 600,000 job openings, which was more at the time than Monster and Hot Jobs combined. Put these on a website which we hosted, which was by our marketing department called flipdog.com, don't ask me why, and launched what became the fastest growing, both in terms of usership and dollar revenue, job opening website ever created. And so you could arrive at this website and search in a way that's quite different than a usual text-based, page-based web search engine. You would specify an area of the country you wanted to search. Let's say we're going to search for a human resources job in Pittsburgh. Specify that you want the Pittsburgh area. Specify that you want human resources jobs. And then get back a list that looks like this, where the results are summarized in terms of the job title and the employer and the location and the date in which it was first posted and things like this. So we and very many users were very pleased with a system like this. So all of the data that you're seeing here is all automatically extracted from the web, these titles and employer names and things like that. So maybe contrast this with another not so shoddy web search engine and how you might approach this problem without information extraction. I typed in human resources in quotes, jobs, Pittsburgh, and you get back hits that look like this. And it's not really what you wanted. Well, let's take another example. Actually, before we do that, so another thing that you absolutely would have no hope of doing with Google is data mining information about job openings. So now that we have a database that says something about what job openings are where, how recently these openings were created, and what categories they're in, we have a database that we can mine, and in fact FlipDog has a staff that does this using both automated and human data mining, and once a month produces something we call the FlipDog Job Opportunity Index, which describes trends in job openings throughout the country. And this report is actually used by several state and local governments to make policy decisions. So something that information extraction enables that you would just have no hope of doing with a regular search engine. All right, another example. Actually, the US Department of Labor saw FlipDog, was very impressed, and asked us to help them with another problem. They were tasked with building a website that helps people find continuing education opportunities. Because it's in all of our best interest to have a well-educated American workforce. This is why NSF is also funding this workshop. They were completely swamped with no idea of a way to do this, and asked us if we could build a system to automatically visit the websites of community colleges and universities and extract information about those courses, which we did.
What courses?
About continuing education courses, so courses that adults could take. Which in practice are not all that different than the rest of the university courses. So we could have done it for those courses as well, but that was not the task. So on the left, you see a snippet of the original web page from the web. And this colored highlighting is applied by our automated extractors. Here finding the title of the course number, the course time and dates, the cost, registration deadline, the instructor, and all this information then would be pulled into a database, and here you see a representation of the slots of the database for this entry. And the data produced by Whizbang is now live on a website provided by the Department of Labor called America's Learning Exchange. And let's say we wanted to search for bioinformatics courses in Maryland. Again, we select bioinformatics and Maryland, and we get back a list of hits that looks like this, showing the provider and the exact course title. And if you click on one of those course titles, you get the different slots that we extracted. all extracted automatically. And again, Google did not, a search engine not based on information extraction didn't do such a great job. All right, so why would we prefer a knowledge-based search over paid search? Well, we're searching over a targeted, restricted universe of hits. So, for example, don't show me resumes when I'm actually looking for job openings. We can give very specialized queries that are topic-specific, that are multidimensional, based on queries of values in particular slots, and based on information that's spread across multiple pages. In the case of courses, the location of the university often does not appear on the same web page as the course description itself, and so you've actually got to integrate information across pages. You get the correct granularity. If you're looking for a job opening that might be described in just a single paragraph, you get just that information versus an entire page, or maybe you're searching for companies described by an entire site. And then specialized display, super targeted summarization in terms of database slot values, as well as the strongest and in some ways I think most exciting, the ability to support data mining. So when you try to solve these problems, when you try to do information extraction to populate a database, a number of interesting issues arise. Right? We've got to follow the right links to get the information that we want, classify pages or other snippets of text into different categories, segment the stream of text into the pieces that we want to fill certain slots. Once we've extracted these individual pieces, associate them together into records. Right? If there are, well, we'll get back to that later. And then once we've built records to remove duplicates, and then this also gives rise to a number of scientific issues, right? Parameter estimation of a lot of parameters from limited and noisy data, which I think all of you are familiar with. Taking advantage of these rich and multifaceted features and structure and formatting information, leveraging local irregularities in the training data and the test data, which I'll describe in more detail later, and then clustering these things. And most of this talk will focus just on these pieces. We'll focus on this information extraction and then these two scientific issues. All right, but before I get into that, let me give just one more example, one that Jason mentioned. So when I was at Just Research, Kamal Nigam, Christy Seymour, Jason Rennie, and I built this system we called Quora, a search engine for computer science research papers on the web. We spidered university and industry research lab websites to find papers in PostScript format, turn them into plain text. It automatically extracted the research paper title, the authors, the abstract, institutions, all of the references, matched references against each other, built a full citation graph, did some analysis of that citation graph, and provided it as a website. And the way that we did, so this website, by the way, will be moving to UMass with me. It's in my basement right now. It doesn't actually work at the moment because it's not connected to the net. And the way that we did information extraction in Quora was using finite state machines. So finite state machines are the dominant method for information extraction, both in industry and in academia. Insight, a company that sells information extraction solutions, uses hand-coded finite state machines. DBN uses some sort of HMMs with some specialized kinds of smoothing. Charles Elkin at UCSD has been using HMMs for information extraction for a while. HMMs beat every single one of the alternative information extraction methods in Dane Freitag's CMU thesis. And in Quora, we used HMMs with a large degree of success. So how does it work? So the HMM acts as a generative model of the header of a research paper. So it's the finite state machine with the traditional parameters for state transitions, the probability of arriving in the state at time, at this state at time t, given that we were in this other state at time t minus 1, and emission probability distributions, the probability of producing this observation given that we just arrived in this state. And these parameters, so the emissions are the words of the research paper header, and we'll set these parameters to maximize the probability of the training observations. We have labeled training data. And for the sake of information extraction, each state is associated with a certain database field. So this is a title state, and this is the degree state. So this acts as a generative model by beginning and start state, randomly choosing some outgoing transition, arriving in the title state, generating some title word, maybe making a self transition, generating another title word, title, author, affiliation, address, date, abstract, done. And along the way, we've generated all the words to form the header of this research paper. And then at test time or performance time, we do information extraction by taking an unlabeled sequence of words, running Viterbi to determine the most likely state sequence, and then any words that were generated when Viterbi said we were in the title state get placed in the title slot of the database. All right, so there are any questions about how a finite state machine does information extraction? So make sure get some basic things right. Yeah?
It's just the unit distribution of the words with each state.
That would be the default, and that is what we used in Cora, that's right. So BBN, of course, has more complicated models and bigrams, and that's what necessitates these other kinds of smoothing. So, yeah?
So how do you capture all possible names or unknown names?
So we had a token for the unknown word, and when you see the unknown word, that's the only evidence you get. In addition, and then there's the context around it, and that's it. So the probability of the unknown word was higher in the author state than anywhere else, as you might imagine, and so on. But we're actually going to get back to exactly this issue in just a moment. Yeah, good. Anything else?
What's the model structure?
Yeah, good. So this is not the. Sorry, the question is what was the model structure? I guess the state transition structure. And so this is an example of one structure that was used. This was not the final structure that was used in Cora. I don't have time to talk about it in this talk, but we actually, as part of this work in Cora, we learned the finite state structure as well, and we did it with some modifications to Stolke and Mahandra's Bayesian model merging. We started with enough training data that it was not possible to do just exactly what they did. We had some additional heuristics and some things like that, but yeah.
And did you start with some labeled data? Because it seems that there is no reason to go completely unlabeled at the beginning. If you could
We actually used only labeled data. We used no unlabeled data. Well, sorry, that's not quite right. The paper describes it a little more. We used this thing that we call distantly labeled data, which I think this community might have already a name for. That's a different name. There was we had some labeled data in which the sequences were labeled, and then we went out to the web and found BibTeX files. And it's very easy to find a very large number of those and get an immense number of words that had been tagged in the BibTeX file as being an author word or being a title word, and we use those to augment the per state emission probabilities. Yeah. Any other questions? Good. All right. So HMMs did very well for us, but still, we had some regrets. Right, so we really prefer a richer representation of text, one that allows us to capture multiple overlapping features or capture situations in which the emissions are whole chunks of text at a time. Let me actually return to your point here. So let's say the word you're looking at is Wisniewski. It's not in your vocabulary. You did not see it at training time. In the old method, it would only be captured as the unknown word token, and you'd have to rely on context to tell you anything else. But if, on the other hand, you captured as part of your model the feature that said this word is in all caps. It ends in the letters SKI. It's part of a noun phrase. Maybe it's in bold font. It's on the left-hand side of the page. And maybe for some other task, you also want to look at features like, well, it's under a certain node in WordNet. Or also be looking at features of the past and present as you're making a decision about the current transition. You would think that you could do a better job. And in fact, in the related work, I'll return to this point and some things that BBN tried to awkwardly do as well. And in other cases, the natural emission is not really an individual token, but perhaps entire lines of text at a time. And these are cases where maybe formatting or some other regular structure like that has a lot to do with it. I'll give an example of this in just a few slides. And so here you might want to ask questions about the line of text like the following. And this is also very difficult to do with the current model. So furthermore, and very intertwined with the first consideration, is HMMs are generative models of the text. They give a probability of the state sequence and the observation sequence. And generative models do not easily handle these overlapping non-independent features. You're faced with a choice. You can either choose to, these features are not at all independent of each other, right? You can choose to model those dependencies, effectively having a little Bayes net inside of each state. That Bayes net captures the emission distribution. Well, that's pretty hopeless, right? I mean, we're already starved enough for training data as it is. There's no way we're going to be able to learn all the parameters of a Bayes net like that. The other alternative is maybe just to assume that all these features are independent, don't bother to model their dependencies, and I'm going to show some results with that later in the talk, and that just worked really badly, and I have some intuitions for why that worked more badly here than, say, it does in 90 Bayes document classification. You can ask them about that. So we would prefer a conditional model, right? One that gives us a probability distribution over a state sequence given the observation sequence. So first of all, this makes sense because at test time we're always given the observation sequence anyway, right? So why sort of expend modeling effort trying to generate something that we're already given anyway? And then furthermore, now that we're no longer responsible for generating all of these features, we don't have to be so precise in how the dependencies between them are captured, and we can have a simpler model that doesn't have to have a Bayes net for each state. All right. Okay, so what we'll do for now is the following. So these are graphical models, right? Not pictures of finite state machines. So these are showing the dependencies among different variables in the system. So in the graphical model for a traditional HMM, right, you have the previous state generating the next state, and you arrive in a state and generate an observation, and you have these parameters. So here, we'll make a conditional model by reversing this arc, making it point up instead, and we'll generate the next state given the previous state and also given the observation with a parameterization that looks like this. And we'll choose to represent this function with an exponential model that will fit in the maximum entropy style using iterative scaling, and so hence we call these models maximum entropy Markov models. And even though we've changed the graphical model, the full graphical model is a lattice that spreads out over the sequence, and you can still do standard leaf propagation, and that gives you algorithms that look a lot like the standard forward-backward procedure, and sort of analogous versions of the Turby and Bell Welch follow naturally from this. So a little bit more about this function. We have to choose exactly how to represent this function, and for the time being, we'll do it like this. So here I've just rewritten that function again. I'll choose to represent the dependency on the previous state by just separate functions for each previous state, which I'll write like this. And then choose to represent this function as I said before, an exponential model, which is written like this. So it's a sum of features and weights. These don't have to be, but are often binary functions that essentially include this weight or not, and then we exponentiate the sum, and this is just some normalizing factor that makes a probability distribution. So,
what does the double arrow mean? It doesn't mean that it's equal, right?
No, it means that this is an assumption that we'll make. We'll choose to. I think this is not a terribly formal use of this, but we'll choose to model this function in a way that I write like this, which means.
In other words, it won't be dependent on st minus 1.
It will. We'll just have a separate function for each st minus 1.
Okay.
Oh, thank you. Yeah, am I blocking the screen too much, and maybe people on the side can't see it?
I don't see it. I didn't see the subscript there.
Okay. All right. Sure.
Oh.
Yeah.
So it's a different.
I apologize to people on the side of the room. Maybe this is better. Thank you. Okay. So an intuitive way to think about what's happening here is in each source state we have a black box that, given the particular observation, produces a probability distribution over possible next states. And when we're in the state and we see that observation, we get this probability distribution, and we choose from that distribution which state we'll go to next.
Normally, the z function is a sum of it's a sum of the exponentials which are shown there.
That's exactly right. So,
but you have it subscripted with st minus 1, while the others don't have st minus 1. I don't know how to explain.
Okay. Well, I
In
think
the exponentiation, there is no st minus 1. And normally the z would be a function.
Should lambda k be subscripted with st minus 1?
Yes.
Oh. Yes, there's a separate, that's exactly right. There's a separate lambda here for each different st minus 1. I'm sorry, that's a typo. So there should be an st minus 1 here.
So it would be a lambda of st minus 1.
There would be a separate set of lambdas for every state,
That's right.
in principle, and then you might die.
For every st minus 1 state.
Yes, yeah.
So it is a lambda of st minus 1.
Yes, that's right. I'm sorry. It's a
Right.
typo. Yeah, thank you.
I guess what intrigues me more is that your z is a function of O, and
So that's exactly because this is a conditional model over O.
right. So
Right.
That means that you can't pre-compute them, for example.
That's right. Yes, that's right.
Just wondering why you chose to have a separate function for each st minus 1 rather than sticking the st minus 1 inside of the feature, inside of the energy thing.
Right. I mean, I think that would be another great choice, and this was a simple first thing that we tried, and that's actually something that I might mention later, but actually capturing this st minus 1 in terms of different features would lend itself to a really easy and natural factored state representation, which I think would be very powerful.
And the other question was, so you chose you're choosing a discriminative model now
Right.
over the former generative model.
Right.
And have you tried, there's another way, which is to stay with the generative model, but change the training criterion to be a discriminative training criteria while retaining the generative model. So I'm just wondering, was there motivation for going to a discriminative model directly rather than doing a discriminative training criterion?
Let's see here. We talked about this at the time, and can I really reconstruct my thinking? I probably not. That would be a great thing to talk about offline. Yeah, thanks. All right, so let's review the big picture recipe before we go on to some experimental results next. So we have some labeled data. We use the labels on that data to lay the sequence down on top of the state model. So label data is assigned to particular transitions in the state model. And now we have for each source state a bunch of knowledge about sequences that at some point were here and then made a transition somewhere else, and we know which observations were associated with those arcs. And so at that point, it's almost like this black box can be trained like a traditional Maxent classifier. I mean, it has nothing to do with sequences. It's just like a regular n-array classifier. We'll train that using iterative scaling or whatever your favorite exponential model training method is, independently for each state. And then now training is done, and then we perform using this new style of Viterbi and then continue like this. All right, any other questions about the big picture?
Just a small question.
Yeah.
Can O be continuous?
I'm sorry?
Can O be continuous?
Yes, it absolutely could. I mean, because these feature functions can be, any arbitrary function of your choice. And in our experiments, these feature functions happen to always be binary, but that's not necessary either. The values of these feature functions could also be continuous values. Okay, so let's talk about some experiments. We grabbed about 38 files belonging to 7 different Usenet FAQ lists, frequently asked questions lists, and labeled each line as belonging to either a head, a question, an answer, or a footer. And then for each FAQ, we trained on one of the files in the FAQ and then tested on the other, and then averaged across all of them.
What are we trying to
I'm sorry. So
test?
thank you. That's right. I should motivate this a little bit. So, wouldn't it be nice if we had question-answer pairs from all FAQs on the web, and couldn't we perhaps use this to leverage a very nice question-answering system? And so, what we want to do is segment and extract question-answer pairs from FAQs. So, we want to recover these labels from unlabeled FAQs. And here are the 24 features that we used. These are features that we came up with on our own through some feature engineering, using just our own intuition about what we thought might be important. We didn't really do any feature selection or feature induction. And I'll let you read through this yourself. But you can see already quickly that these are not at all independent from each other. There are a number of overlapping features. Okay, and we tested these 4 models. So this is a stateless maximum entropy classifier, right, that has no notion of the sequence. It makes a decision about each line independently from the others. This is a traditional HMM in which the emissions are the words. This is the same model, also in HMM, but the emissions here will be the results of running each of those 24 feature tests. Almost as if we took each line of the FAQ and replaced the text in that line with a list of tokens generated from each one of the features that said true to this line, and restricted the model to not make a state transition except on line values. And the maximum entropy Markov model is the model that we've been talking about so far, that uses these features and is a conditional model instead of a generative model. And here are the results. And so let's talk about some things that these show. So, well, let's see here. What numbers are we looking at, first of all? So precision is, right, it's the number of correct segments divided by the number of segments predicted. Right. And recall is the number of correct segments divided by the total number of true segments out there in the labeling. And so in both cases, higher is better. Value of 1 is perfect. And what we see here is that, well, state really matters. Both of these values are pretty lousy. Right. Performance, I guess, precision improves when we know something about when we capture something about the sequences. Although recall decreases. I mean, in general, this performance is pretty lousy also. This tells me that the words themselves are not all that important. When we move to looking at the features instead, performance rises. And so this says that these, the information about how to do the segmentation correctly is really captured quite well by these features. But when we use a conditional model instead and don't make this independence assumption about the features, recall increases and precision more than doubles. So we were very pleased with these results.
And for a segment to count as correct, you have to get start time, end time, label all correct.
That's right. Yeah, there was no
So
partial credit.
If you broke up one true segment into 2, but you labeled, if you labeled them both correctly, you still wouldn't get credit.
That's right.
So if the answer was 50 words and you said first 25 words answer, second
That's
25
right.
words answer.
Yeah, that's right. Yeah.
What would happen if, for example, you increased the number of states in the first 3, or
I'm sorry?
if you increase the number of states in the first 3 models, or, for example, increase the capacity of the O distributions?
Right. So varying the number of states in the model is not something that we experimented with. All of these models.
Sorry, say again?
So varying the number of states in the model is not something that we experimented with. Is that your question?
You didn't experiment?
We did not experiment with
Okay.
varying the number of states.
Okay.
Yeah, sorry.
Model.
All of these models had just 4 states,
Just 4
one
states
for each
with the
label.
same, yeah.
That's exactly, yeah.
Okay, so maybe you mentioned that this mistake that this seems to be more like a detection problem. What was the in the first part, in the maximum generative model case, what was the discriminant function? You would calculate the likelihood and then decide using a threshold whether it's a Q or a pair?
No, it was, I mean, information extraction was done by the same method as I described in the slide when we were talking about Cora. There was an HMM that was a generative model of the text in these FAQs, and we ran Viterbi, and words that were generated when Viterbi said we were in the question state were labeled as belonging to the question. Yeah.
If you had 2 questions in a row, nothing in between, would that be one question segment?
Yes. Yeah.
When you did the feature HMM, did you generate all the features for a word simultaneously, or
Well, I think there's, let's see here. No, they were generated in serial, but with the restriction that you couldn't transition out of a state unless you were crossing a line boundary. So it was, I mean, the order of them didn't especially matter. Yeah.
I don't know what line boundary is. What is line boundary?
Oh, I just mean a new line. I mean, it was ASCII text, and it was.
Oh, line. I mean.
I'm sorry. Yeah, literally a line of text. Thank you. Yeah.
Sorry.
Yeah.
So the units that these models are working with, each observation is a whole line.
That's exactly. Well, yes. I mean, with these, very clearly, that's true.
Right.
Here, that distinction is a little bit less clear, but with this restriction of only leaving a state on line boundaries, I think yeah.
Because your features, for example, are line features.
That's right.
Some
That's
of them
exactly
look
right.
at individual words,
That's right,
others
yeah.
count.
Yeah, that's right. And this is another reason that a generative model can be especially hard, right? I mean, when the features you want to use are of lines as a whole, and then if you were going to do a generative model, your mission would have to be a line as a whole. And how is it that you can define some multinomial distribution over all possible lines in text in the universe? It's just incredibly difficult.
So is then a line not a specification of the words in it, but a specification of the collection of features that the whole line contains?
I mean, that's how I would describe. Yeah, when we use those features, that's how I would.
No,
Yes.
but in the last one,
Yes.
There's going to be some capitals and there's going to be some numbers, etc. And so then the line is characterized
By
not
the set of-
sequentially
Well, so
by collection.
well, it's characterized by these 24 features, and it's these 24 features that form the sum in the exponential model that I described in the
But
previous slide. The order
this
doesn't matter.
number refers to the line beginning.
That's correct. That's correct.
And what does blank mean? Does that mean?
It means the line is blank. It contains
the
a
whole
new.
line, not that there is a blank included. Or
No,
something.
these are all descriptors of the entire line.
So
As a
then
chunk.
more concisely, your O sub t is a line, and this is a function of O sub t.
Correct.
as
No, also,
Correct.
O sub t is specified by the collection of features that belong to the line. Is this correct? And there are no.
So now we're talking a little bit more about notation, right? I mean, the way I wrote things before. Here we go. Sorry, was that those 24 features are described by these
Yes.
different FKs, right? And so maybe we call this O is the text of the line itself, and then these are various yes/no questions about the text of the line.
Yes.
Okay. All right. And we're getting a little bit concerned about time.
Yeah, go at the speed.
Yeah. Okay. Yeah. There we go. Okay. So let's see. So here are some results. Okay. So we were quite pleased with these results, but again, there's a problem with these models. John Fernando and myself called it label bias. The problem has also been brought up by Leon Botu and others, and it's in some ways counterintuitive and complicated, and many people, when it's explained the first time, don't really get it. I'll give it my best shot through the following simple example. And I would welcome additional help from other members of the audience who are familiar with this problem. So let's say that we're going to have a very simple HMM for doing the following extremely simple speech recognition problem, which is just to recognize words in this two vocabulary system, rod or rib. And so we have a finite state model that looks like this, and these are representing hearing these different sounds. And first, let's talk about how an HMM would solve this problem. So we'll start at the start state, and let's say that we're going to observe the sound sequence rib. Okay. So we'll start at the start state. We'll observe the R sound and sort of it's almost like the probability mass that's going to be flowing through these transitions as part of our Viterbi calculation. Will get split equally between these two. I should stand over here. I'm so sorry. We'll get split equally between these two states. And I'm sorry. With an HMM, first we'll make the transition probability. Maybe these two transitions will be equally likely because maybe we saw these words equal number of times in the training data. So our probability mass gets equally split here. And then we observe the R sound. So we multiply that probability mass by something, but it's the same thing in both cases because both these states pretty much only produce the R sound. All right. Then we make our next state transition. Well, there's only one choice here, so all of our probability mass goes on to the next state in each case. And now we observe the I sound. Well, this state is incredibly unlikely to have generated the I sound, so the probability mass that arrives here gets really downweighted. This state was quite likely to generate the I sound, so the probability mass stays pretty much intact and continues on, and the HMM correctly says, we just heard the word rib. All right, now let's think about how a conditional model does this. We'll talk about it in terms of the MEMM, but actually any per state normalized conditional model would have exactly the same problem. All right, again, we'll start here in the start state, and we'll observe the R sound and come up with a probability distribution over possible next states. Well, both of these states could produce the R sound, and so again, our probability mass will get split. All right, so there's some probability mass sitting in this state. Now we observe the I sound, right? All right. So we've got a function. Think about the functional form of our model. It's responsible for producing a probability distribution over possible next states given the observation, right? There is only one possible next state here. We've observed the I sound, and observing the I sound on this transition, just perhaps never really happened in the training data. But remember, we're not generating the I sound; we're conditioning on it. So we may have, we're conditioning on an incredibly unlike, on an observation that we never really saw. But that doesn't change the fact that the model has to give a normalized probability distribution over possible next states, and there's only one possibility. The model has no choice but to pass all of its probability mass on to the next state. Let this sort of sink in a little bit. So the end result is that this conditional model cannot distinguish between these two state sequences when given the observation R and B.
But of course, you could have a transition from one R to either 0 or I, and then
yes,
you're back.
That's exactly right. Now you might end up with some pretty odd state sequences that you might not have intended. If you actually perhaps intended there to be semantic differences between these two states, you might end up with a state sequence that goes like this.
I think what Brett means is you can determinize this machine and have a solid problem in this particular case.
Yes. Okay. Good. So I mean,
Yeah, that's right.
and I'll get to that in the next slide. But yeah, let me just ask if there are any other questions about this labeled bias problem. It's a rather odd thing.
Well, it might be worth mentioning actually that this
Yeah.
problem is not unique to finite state machines. It also shows up when you're conditioning any sequence of decisions on fixed input. For example, there are generative parsers and there are parsers which condition some sequence of decisions, each based on the structure built so far, and you get the same problem with splitting the probability mass without looking at it.
Yeah. So things like Adwaite's parser has exactly this problem
Exactly
also.
right. Yeah.
Right. Yeah. And in fact, so there's some interesting things about it. I mean, like Adwaite getting better performance when he really narrowed down the beam in his beam search, and narrowing the beam is exactly sort of an ad hoc way of one ad hoc way of addressing this problem.
The point I've missed is why would you start with two different R's?
Yes. Okay. Good. Okay. So I should go on to my next slide then, maybe, which is just going to. Okay. Good. I mean, so maybe I can just sort of make sure I address these 2 points. So, in a way, we're biased towards states with few siblings, right? In places where the parent state had few choices for where to pass its probability mass, it's sort of artificially restricted in some ways. And so part of this is, if everything was fully connected, then we wouldn't really have this issue. And then, in essence, it's the per state normalization here that's really causing this to be a problem. The restriction that this state has to come up with a normalized probability distribution over possible next states. All right, so there's some possible solutions, right? So one is to determinize. And actually, in this case, exactly like you're saying, we just collapse those 2 R's. We delay our choice points until the point where we actually see an observation difference, and the problem goes away. And in this case, it actually makes the model smaller. Wonderful. But in general, determinization is not always really possible, especially when you're dealing with weighted finite state machines. It just gets very hairy. And then also in general, the size of the state space grows dramatically, not shrinks. So these are some difficulties and regrets. Another solution is to use a fully connected model, absolutely. And I think this is why we did not really see the label bias problem in our FAQ segmentation task, because that was a 4-state fully connected model. But in general, and actually Dane Freitag and I have this little paper on this, that for information extraction, I'm sure for many other tasks, being able to use some prior knowledge to create a specific state transition structure can have a big impact on performance. Forcing yourself to use a fully connected model removes the possibility of using this prior knowledge in building the structure. So our solution is to use a slight modification of these maximum entropy Markov models, which we call conditional random fields. They're probabilistic conditional models that generalize maximum entropy Markov models. They allow some transitions to vote more strongly than others in computing the state sequence probability. And it's a normalization over an entire sequence rather than a normalization on a per state basis. So let me try to say in a little bit hand-waving terms what I mean by these last 2 points, and then in the next slide show some equations. So in maximum entropy Markov models, they're really they're normalized probability distributions at each outgoing state. And you can talk about the parameters of that result from each of these sums of these exponential sums as being probabilities. So here we're going to remove that restriction, and the weights by which these Viterbi scores are passed from state to state will no longer be probabilities. They'll just be numbers. And they'll only get normalized into probability distributions when we have an entire path. So we'll normalize over whole sequences instead of over individual transitions. So, okay, let me just say this in a different way. In the NEMM, as in also HNMs, right? You normalize everything on sort of a per parameter or per state transition basis, and and as you go forward and calculating the probability of a particular path, you multiply together a bunch of numbers, and what you have in the end is a probability, because all the constituents along the way are all probabilities. In this new model, all the constituents along the way will not be probabilities, and when you just multiply through this path, you'll get a number that's not a probability, it's just a number. And if you want to normalize to get the probability of this path, you have to divide by the probability of all alternative paths. And that will give you the probability of this path.
Which you can't do.
Which you can do because sort of dynamic programming.
It's so enormous that.
So again, so the trick is that just as in HMMs, dynamic programming comes to the rescue again, and it actually all works out quite nicely.